Today we're going to start our probability unit. Before we start calculating and talking about probability, there's a few keywords that we need to discuss. The things that we're going to be talking about today are sample spaces, the FCP, which we'll learn about in a few minutes, and simple events. The sample space is a list of all possible outcomes in a probability experiment. So the sample space are the outcomes. So for example, if I go to Marble Slab, my sample space are the different flavors that they have for me to choose from. It's the different outcomes that I have to pick from. There are many ways to organize data when constructing a sample space. Tree diagrams and tables are a few ways that you may already be familiar with. Tree diagrams is something that we practice with in 6th grade, so this shouldn't be anything new for you guys. The first example asks for us to make a tree diagram to determine the sample space. At Marble Slab, you can order vanilla, chocolate, or strawberry ice cream in a cup, sugar cone, or waffle cone. List the different combinations you can order. There's a couple different ways that you can create a tree diagram. You can either start out with your flavors first. So I'm just going to abbreviate V for vanilla, C for chocolate, and S for strawberry. And then you can go down and give each one of those flavors an option of cup, sugar cone, or waffle cone. So cup, sugar cone, waffle cone. For chocolate, I also have those three options: a cup, a sugar cone, or a waffle cone. Same thing for strawberry. I can have a cup, a sugar cone, or a waffle cone. I want to show you another option for creating tree diagrams. I can go horizontal, so I can make my tree diagram come out to the side like this. I'm going to show you an example like that, but instead of choosing my flavors first, I'm going to start with the type of dish it's going to be in. So I'm going to start my tree diagram this time with cups, sugar cones, or waffle cones. And then my actual tree branches for that are going to be my flavors. So vanilla, chocolate, strawberry. Vanilla, chocolate, strawberry. So those are just showing you a couple of different ways that tree diagrams can be drawn. If you ever have a question like this, it may be presented vertically or horizontally as multiple choice. So it's just good for you to be familiar with the different ways that a tree diagram can look. Example 2. Wade's grandmother has a candy dish with 7 candies in it on her living room table. The table shows all the possible unique outcomes if Wade was to choose 3 candies at a time from the candy dish. Based upon the table, how many of each type of candy was in his grandmother's candy dish? So if we look at our options, we have different flavors. I see cinnamon, peppermint, wintergreen, and butterscotch. So those are the 4 different flavors that we have, different types of candy. The question's asking, based upon the table, how many of each type do we have? So take a second and see if you can figure that out. It looks like we have 3 cinnamon, because I was able to get 3 cinnamon at one time. The most peppermint that I'm ever seeing at one time is 1. 1 peppermint at a time, 1 at a time. So there must only be 1 peppermint candy in that dish that I was only able to pick 1 each time. For wintergreen, the most wintergreen that I'm seeing at one time would be what amount? Good. 1. And then butterscotch has 2. You can see in the last row, you were able to pick 2 butterscotch with a wintergreen. So you must have 2 butterscotch candies in the candy dish. The FCP, what those letters stand for, are the fundamental counting principle. This is used to find the number of possible combinations or outcomes. To determine the total number of outcomes, we multiply the total number of each situation. Jackets come in red, blue, or green, and in sizes small, medium, and large. How many possible outcomes are there? So rather than having to draw a tree diagram or list out all of your combinations every single time, the FCP is kind of like your shortcut. So if we look at each of our different situations, I have color and I have size to choose from. Color, I have 3 colors, red, blue, or green. And in sizes, I have 3 sizes, small, medium, large. So if I multiply each of those situations, I have a total of 9. If I were to actually list these out, red, medium, red, small, red, large, green, medium, green, small, green, large, and so on, I would end up finding out that I would have 9 different combinations to choose from. So the FCP is just your shortcut mathematical way to solve these types of problems. At Fuzzy's Pizza, you can order your pizza with thick, thin, or hand-tossed crust. They have small, medium, and large sizes to choose from, and cheese, pepperoni, or sausage, hamburger, and Canadian bacon toppings. How many different combinations of pizza could you order? So let's think about our choices. We have to choose what type of crust we want. And there we have thick, thin, or hand-tossed. We have 3 options. Then for our size, we have to pick what size pizza we want. Small, medium, and large. Again, 3 choices. Then for our toppings, assuming we're just going to have a one-topping pizza, we can choose either cheese, pepperoni, sausage, hamburger, or Canadian bacon. So on toppings, we have 5 choices that we can choose from. Now I'm going to multiply these numbers. 3 times 3 is 9, and then 9 times 5 is 45. So in this situation, I would have 45 different choices, 45 different types of pizzas that I could choose from. Example 5. A test consists of 5 true or false questions. How many possible outcomes are there? So let's think. We have 5 questions. Question number 1, question number 2, question number 3, question number 4, and question number 5. Each problem is true or false. So each question has 2 answer choices, true or false, true or false, true or false, true or false, true or false to pick from. So if we multiply all of these values by one another, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and 16 times 2 is a value of 32. So there would be 32 different combinations. You could have true, 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 false, 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 true, true, false, false, false. All those different combinations, all of those different orders that this could appear in. 4 coins are tossed. How many possible outcomes are there? So here's like my coin 1, 2, 3, and 4. 2 outcomes, heads or tails. 2 outcomes, heads or tails for every single coin. So if I toss all 4 of these, I'm just going to multiply those 4 2s. 2 times 2 is 4, times 2 is 8, times 2 again is 16. Last year we also discussed the difference between theoretical and experimental probability. So theoretical is what should happen. If I flip a coin 10 times, I should land on heads 5 and tails 5, an even split. But experimental probability is what actually happens. If we were to actually do this, flip a coin 10 times, is it guaranteed that we're going to get heads 5 times and tails 5 times? No. So theoretical and experimental probability are usually not going to be the same value, because what should happen and what actually happens is not very common that they're going to be the same. So for the following examples on a number cube, which is just our dice, so think of a number cube as your dice, which has the numbers 1 through 6 on it. This dice is going to be rolled 50 times. And we can see in the table, they show us how many times it landed on each number. So using the graph, find the experimental probability of rolling a 2. So we can see our 2 was rolled 8 times out of the 50 times total. If I simplify that, divide 8 by 2, which is 4, 50 divided by 2 is 25, and that cannot be simplified any further. So remember, this is all theoretical because I'm using, this is all experimental because I'm using the table that they've given us. What is the theoretical probability of rolling a 2? Well, theoretically, if I think about the numbers on my dice, 1, 2, 3, 4, 5, and 6, I only have 1 2 on that dice out of 6 total numbers. So theoretically, the probability of me rolling a 2 is 1/6. Whereas experimentally, according to what they've given us in the table, that one was 4/25. Using the graph, find the experimental probability of not rolling a 2. So we want to think about 1, 3, 4, 5, and 6. Everything except for the 2. So if we were to add those all up, we would get 42 over 50. I can divide both of those by 2 and get 21 over 25. Always in probability, make sure that you have your fractions in simplest form. Example 10. What is the theoretical probability of not rolling a 2? So let's look at our options. Theoretically, what should happen? I have a dice with the numbers 1, 2, 3, 4, 5, and 6. I want the probability of not rolling a 2. So I could roll a 1, a 3, a 4, a 5, or a 6. So that leaves me with 5 numbers I can land on except for a 2 out of the 6 numbers total. Again, you can see that this theoretical and this experimental probability are not the same. Using the graph, find the experimental probability of rolling a 1. So back up to my graph, there were 10 1s that were rolled out of 50 total. Divide 10 by 10, you get 1. 50 divided by 10 is 5. Using the graph, find the probability of 2 or 1. So in math, that or means to add. So the probability of a 2, well, we had how many 2s? 8. 10 1s. So 10 plus 8 is 18. So I'll take either one, a 2 or a 1, out of the 50 times total, and then simplify that down. 18 divided by 2 is 9. 50 divided by 2 is 25. And that cannot be simplified any further. The last example says, using the graph, find the probability of an even number. So let's go back up to our graph. I'm going to this time just highlight my even numbers, 2, 4, and 6. So I don't care which even number to land on, 2, 4, or 6, as long as it's one of those. So this is kind of like one of those OR problems where I'm going to add 8, 9, and 12. So back down to our problem. If I have 8, 9, and 12, that gives me a value of 29 out of the 50 times that it was rolled total. Because 29 is a prime number, I cannot simplify that fraction any further.